As discussed in the preceding chapter, both Verilog and VHDL have evolved into languages that offer maximum flexibility of implementation to designers by providing multiple layers of abstraction. It is worth noting that the level of human comprehension tends to be inversely proportional to implementation complexity. Verilog and VHDL primarily offer 3 layers of abstraction for implementing a digital circuit. Generally, only a few companies focusing on deep optimization of their intellectual properties, IPs, engage in cell library implementation using hardware description languages. However, in contemporary design practices, mainstream companies are also exploring high-level synthesis based on their use case requirements, for example, in design of 5G chips. This is often implemented in C++ and then converted into HDL code by high-level synthesis, EDA software. To better understand the 3 levels of abstraction, let's consider a practical example of baking a cake. In the behavioral approach, there is a high-level instruction with few details, allowing for creativity and decision-making. In the RTL level or data flow approach, there are much more details, especially related to how the actual process flows, what comes first, what comes next, and in what portions. This provides a better understanding of how to bake a cake, hence helps with the outcome as per expectations. Moving down into the gate-level abstraction, we can quickly see the increase in complexity. There are instructions and rules that control every aspect of the baking process. Although this might yield a masterpiece, it might be a very tedious and time-consuming process to follow. What if we need to bake 100 cakes a day? The complexity and effort required quickly becomes unmanageable. Now that the concept is much clearer to you, if you'd have to choose between each of these, which level of abstraction would you choose for designing a microchip? Before you choose, here is a hint. It is essential that the digital circuit realization be in a synthesizable format. The verification infrastructure, however, need not be synthesizable, but should be faster to implement. So now, what would you choose? Here's how the industry has utilized each level of abstraction. Behavioral gives less control over the design elements and flow of data inside a circuit, but it's super fast to implement and designer does not need to worry about too many details. It's a clear winner for digital verification. Hence, verification engineers, in contrast to design engineers, write a lot of behavioral code for the test bench and the tests. Data flow, or RTL level, provides enough control over the design, has good comprehension, and has an average implementation speed. Hence, this is the most desired level of abstraction by digital design engineers to realize a synthesizable digital circuit. The gate-level abstraction is typically not used to design large digital circuits by engineers. Instead, RTL design is converted to gate-level design by specialized synthesis software tools. And there you have it, various levels of abstraction that HDLs provide and how they're utilized in the industry for designing of circuits. This was a basic overview of this topic. Join me at the IISEED's Advanced Designer course where I explore more deeper aspects of this topic. Here is a sneak peek of what you learn at the Advanced Designer course. There is truly a differentiating, industry-led approach that not only helps you to become a master of RTL design, but also prepares you to face interviews and get job-ready at premium semiconductor and design firms. Explore the entrance exams and check your eligibility for this course at www.iseed.com. Thank you, and I will see you in the next one.